range of really fascinating new material areas, as well as nanotechnologies and other technologies. So I'm just going to hand over and learn a bit about the work that we're doing. Thank you.
Did anyone drink it? Did you?
No, I
Okay. Well, maybe now for something a little bit different. I'm going to give you a whole load of slides here. And the reason for that is you can take some of it in, but you can get in touch with me, and I'll be happy to send them out to you afterwards. P-Cube first of all, stands for printable, paintable, programmable materials that are capable of constructing intelligent systems. And I'm going to talk about this through the convergence of biology, materials or polymers, printed electronics and human ecology, but as a driver for product and service innovation. I'll come back to that. So what I'm going to talk about, the introduction, the convergence of bio, info, nano, cognoscience and technology, products, services, experience that respond to human needs, new materials, innovative technologies, which is pretty much what I've said of this. Current activity in my group in P-Cube Design, STEM, Interaction Studio, and some conclusions. So, emerging ambient technologies in the 21st century, and here's the first key, putting the citizen at the centre of technology. Soft machines, living with informed complexity to make life easier, safer and healthier, have purpose. So we do that through looking at the ability to create new space for product innovation, needs and concerns aligned to useful materials and technologies through critical design probes in the group, and products and services that matter in people's lives, otherwise pretty pointless us doing what we're doing. Just a view of consumers and communities. We use this idea of 3 Ps, people, planet, and prosperity, and look at that as a creation of the vision of what can we do with design, creative design, and innovative technology. So building product solutions from the molecule up, a platform for materials exploration and innovation. And I'm grateful to George Post for giving me a few overheads here, because George has some fantastic images which I couldn't put together fast enough. So the evolution of production through agrarian production, and then industrial, and now, of course, digital, and even into post-digital, which is maybe neo-human. And it gives us a platform for materials exploration and innovation. And a lot of it emanates from, especially in between the wars, with companies like ICI, DuPont, Celanese, born in a test tube. This was about materials being born in a test tube. Textiles, plastics and chemicals in 1937. Wool and cotton, of course, and then onto wood, and fibres and paper, and then polymers and plastics, synthetics, which have now moved into a realm of super synthetics, which I'll come to. So soft machines is hybrid ecosystems. How and why our future products take shape, defined by applied design and engineering, that in turn is informed by advances in our STEM world, science, technology, engineering, mathematics, that provides us with the ingredients and toolkits with which to transform concepts to artifacts. And the context of this, it's interesting listening to Suzanne's view of this and definition, is in our case materials moving from scientific function, polymers, films, passive to active, to responsive, to adaptive, to conversational materials that can converse with individuals and understand individual personalities, through to sensory, emotive, aesthetic, emotional and cultural effects, and those then looking at different product areas. One of the key areas here is what the most trusted material on the planet, because as I look at you, you all have decided what you want to wear today. And that's because you trust what you wear. You don't expect it to poison you, you don't expect it certainly to kill you. So it's trusting. And textiles, through natural proteins and cellulosic materials, wool, silk, paper, wood, and then synthetic polymers, and now supersynthetic. Supersynthetics mean conjugated conductive polymers that are capable of creating memory and logic. And they look just like that. And I'll come to that. That's really interesting. We can create logic, and we can create memory from a fluid that just looks like that. So we can print it, we can paint with it, and we can make it understand who it is that's dealing with it. So creative manipulation, experimentation, exploration, and exploitation, and demonstration of it real effects, and connecting science with sensory and emotion. And that takes us into this area of bits from bits, the proliferation of digital design and fabrication as well, cyberspace to connected space to biospace to simulation space, and then into threat space. What's good, what's bad for us. Disruptive technologies, which can often be different, but we don't know they're going to be better. And this comes about also looking at the idea of impact versus time. The good science that was done through 1930 to 1960 in solid state physics had very little impact. What did have impact is the microelectronics revolution that stemmed from it. The same with bioscience, and what is the impact comes from biotechnology and its use directly for human benefit. And now we have this idea of so-called nanoscience and nanotechnology giving us functional materials and useful products. Is that real? Will it be real? I think someone mentioned at the very beginning about synthetic biology. It's the same in nanotechnology. The idea that these things happen because you mention the word doesn't. Maybe in the next 2 decades we'll see that happening. But looking at the audience, most of you are quite young, so I think you probably have a chance of having a career in this. So advanced manufacturing technology, vectors, technology convergence, life science, engineering, materials, robotics, computing, what's called GNR, genomics, nanotechnology, and robotics, one of the big plus phrases. Multi-scale design, simulation and fabrication, different length scales from nano through micro to meso to macro. I'll come to that again further. Dramatic expansion of the design space, escalating distribution degrees of design freedom, increasing complex autonomous systems, combinatorial assembly of increasingly diverse materials, and self-assembly and self-repair, and learning from biology, and being inspired from biology, and then synthetic biology, directed evolution, and exploring biospace. And the reason I put that up first is this, that there are real drivers for this, though, economically and societally. The citizen at the centre of technology, long life population, quality of life enhancement, and emotions of populations, from telemedicine to convenience to ambient assisted living, and digi-boomers to renewable energy to non-invasive surgery to smarter homes to 50 is the new, 50 is the new 70, or 70 is the new 50. Intelligent consumer products through fashion and lifestyle, product design and experiences, and now social networks, and personalised medicine and customised beauty, where we can look whatever we feel like. But all of this is tampered with this idea of things that we conceive of as being really useful, wherever it is geographically. Its realization is often takes a long time to digest, so that the zip, which is a really useful thing, 1883 to 1913, 30 years. Mobile phone, actually, the brick in 1970 to 4G in 2015, complete 4G, 45 years. So now, where is nanotechnology, where are wearable sensing and wearable technology is going to lie in that? Never mind synthetic biology and the ability to shape it out. So a little bit about nanoscience, because just to let you know how we got into this, the reason that it all became really popular, apart from one or two things in the 50s and 60s, was you were able to have new ways to see and measure at the nanoscale, 10 angstrom scale, 10 atom scale in the 1980s. And then, even more important, new ways and new tools to sculpt material at the nanoscale, at 10 nanometers in the 1990s. And there is actually only one genuine nanoscience and technology company, only one, that's Intel. Intel produces its basic core transistors of a size which is half the diameter of a cigarette smoke particle. And they do it by the trillion every day. That's a genuine nanotechnology company. But we, all of us, are macro, the human experience. We understand through repeated experience and over time the accumulated experience becoming intuition to us. The ultra-large things and very, very small things, however, are not understood in that way. Now, maybe one idea about nano. Your fingernails grow at 1 nanometer per second. All of us. And when you work that out, undergraduates get straight on it. It's about 3.2 centimeters, so about 1 and a bit inches in a year. But the interesting thing is that that 3.2 centimeters is exactly the same amount of growth that occurs in Mount Everest in a year. So the nanoscale is the same, across those length scales, in terms of the kinetics. But nanotechnology, if you want to take away one thing about this, is that it is an additional innovation toolkit to what we already have. So we have unique properties that can be generated at the nanoscale, and so long as there are potential application spaces, it will take on. And if they can't be found, it will be, as Suzanne said, it will disappear. There are certain things come and gone already because they can't be taken up by the human as being useful, and or it will resonate with the human. So the human-central technology, again, I deal with nanoscale length scales from the airport, what happens to humans in airports and hospitals, at the kilometre scale, to the house at the tens of metre scale, to the car at the metre scale, to furniture at the tens of centimetre scale, to clothes, and then into the body at 10 to the minus 6 and below. 10 to the minus 6 to 10 cubed, another 10 to the 9 grouping of length scales. The human at the centre of technology. So let's have a look a little bit at where we sit, because I have a group of 10 people working in who are creative designers, who have come from groups such as Central St Martin's and Royal College of Art, and innovative technologists who've come from industry and from academia into the group. So we'd be looking at the future of fashion and active living. And if you think that's trivial, fashion means lifestyle, lifestyle goes to wellness, wellness goes to healthcare. You go from design to STEM. It's a diagonal that's been with us forever, and it will always be with us. Because all of you here have your own idea of fashion and lifestyle and wellness and healthcare and active living. So some of the external factors then that affect this is climate change, change in supply chain, social, ethical raw materials, sustainability issues, and aging populations, lifestyle trends, medical trends. Now, the design factors we have to look at in terms of how we relate materials through design, STEM interaction, through form and style, maintenance and end of life, performance and costs, and physiological needs. And form and style, culture of activity, future leisure activities, commercial space, new apparel, new sportswear, driven by Paralympics technology, aging populations, contemporary fashion aesthetic. What will clothes look like? Pace and duration. Can you build spatial and temporal effects into clothing that change with time? Mass customization and then slow versus fast fashion. And here's an example of a biosuit, this side of safety, security, space. This is worn by Davos Newman, and we're working with a group in Cornell looking at long-range space travel and long-range space apparel, and looking at the idea of bio-second skins. that will allow us to take the things that she's wearing here and make furniture from them, and then take that furniture and make other products over a 30-year space journey. Maintenance and end-of-life materials, repair, recycle, degrade, durability and cleanliness. Using inspiration from nature, the lotus leaf, and understanding that the lotus leaf works as an effective cleaner and removal of dirt because of nanoscale perturbations on the or roughnesses on the surfaces of things that we think are very smooth. Fermenter-grown clothing. This is by Indrio, and it's based on polylactic acid biopolymer. And basically, going back to the first talk today, this Du Culinaire Workplatz, their project on tasty unwearables. So maybe we can wear this and maybe eat a sleeve afterwards. But it's very interesting because it can be quite beautiful and aesthetic, but it is made of biological material, but made in such a way that it's telling different types of stories. And of course, you can also print food. You can. We're working. This happens to be a nice. This is the $10,000 3D printer. It's a typical Perspex printer where you can print food, and you can print the texture, and you can print the morphology of that food. And here's an example again of a fish that sharks avoid because its scales are too tough. And that's basically a proteinaceous glue and silica that allows these scales to be so tough that if the shark bites into it, this fish survives. So bio-armor is an interesting topic. And then physiological needs. The idea of ergonomics, functions, demand of activity, the needs of the body, and additional functions. And I can put this in the context then of this design-science interaction. How do we embed intelligent, yielding technologies into societal and commercial frameworks, enhanced by materials and devices, but driven by the development of printable electronics and conformable and responsive biomaterials? And it's written here as assets in life, phases in life, and aspects of life. And that gives us the topics that we can work on in terms of looking at solutions-focused ideas. So taking design fiction into design fact, validation through making. Making materials that matter, explore, investigate, question, and demonstrate the future role of biology, plastic electronics, and polymers. The quality of material experience, which is to do with the heart as well as the head, and the emotional usefulness of products and services. And this is done basically by looking now at the idea of the inexorable move towards softer, more flexible, so-called smarter and wet materials that can operate in the wet. Functionality in all aspects of life, really. Communication, well-being, mobility, and differentiation. And this is the bedrock of what we do. These are the 12 families of materials that we are getting used to and getting used to using. Electrode photoactive polymers, bioresponsive hydrogels, electroluminescent fibers and films, and photovoltaic and photonic fibers and films. A photonic fiber allows us to make colour through structure and never have to use a dye. And that's massive in certain industries where you don't have to use water and contaminate it. And then biomimetic inspired materials, and then counterintuitive materials like a metamaterial. The most common metamaterial is something called an auxetic material. I'm not sure if you know what that is, but when I look at you just now, looking back at me, there's auxetic materials everywhere. And the most common auxetic material is human skin. So when you stretch an auxetic material, it gets fatter. Right? And that means that's why we don't shed skin like lizards. We can do this for 85, maybe now 100 years, and it doesn't come off. What actually happens, the strain rate gives us slightly fatter positions on the joints, which absorbs energy all the time. So auxetic materials is a really interesting material. And there's a number of new classes of these non-counterintuitive effects becoming available. And then stretchable electronics, swallowable electronics, and then silicon-carbon integration. And these go together with shape memory alloys and shape memory polymers, and then chromogenic, color-changing, optically changing materials. So these are the matrix of 12 foundries that we use in experimentation. The reason being is this graph, and I still use this from John Shaw's work, that everything to do with silicon at the top of that diagram, silicon wafers, is through its mobility. That's the amount of free electrons in its structure which allows things to be turned on and off as a binary code. And this binary code, this ability to have electrons, allow you to turn something off, a yes or a no, 1 trillion times a second in silicon, and that gives you all the binary code you'd ever need. That's why it's used in today's processors. These materials called conjugated conductive polymers started off, they could operate and be changed once a second, but over a 20-year period that's now become 100 million times a second. And to turn something on and off, a yes or a no, 100 million times a second gives you all the binary code you need to do all those things in the green that you can see. So we can now start to think of ambient electronics as the basis for responsive and interactive electronics that can be made into any shape or form. And to do it cheaply, like this. And to spray it, to paint it, and to coat it. The way we look at this in the group, my own group, is through the side of dots, lines, surfaces and structures as a design approach at PQDI to work through the length scales. I'll give you some ideas. Here's an idea of dots. Dots are dyes and colours that can be made into solution phases that look like water. And we use research 2 and 3D inkjet printers to look at making structure from these materials. And a classic example of how you take that to an extreme is the fact that there's no colour on any butterfly, but the butterfly itself has on its surface dots. The dots are basically periodic photonic crystals, and those photonic crystals in visible light only react to one frequency in that light, and it changes its energy level and gives off a colour in the visible energy spectrum as it changes. And all butterflies are dull grey. That's not good. And then from lines and how designers will knit and sew and weave with lines to using basically sophisticated digital 2D, and in this case 2D jacquard, but also 3D weaving of materials, which can be what we call awkward materials. And as I was saying to Suzanne on the way down, one of our PhD students is working on quantum weaving. She's trying to weave with things that you can never see. And that's quite interesting. It's just to do that under an atomic force microscope. So I'm now taking the risk as a chemical physicist of letting a designer from RCA use an atomic force microscope to weave. I'm not sure. But we'll get there. And there's another example of using 3D sewing. And then the surfaces, where on the left-hand side, our typical large area screen printing facility, and then screen printing on a A6 Epsilon colour printer onto textiles. And then into structures, this was made 2 years ago, these shoes that were made with a 3D printer. And when I did this at RCA, we also we tricked the model who came in to the catwalk show. The shoes on the right-hand side, we put a sensor in the bottom. She put the shoes on, the sensors weighed her. On the screen it said, "You're 1 kilogram too heavy, can you please go out for a jump for 10 minutes and come back?" And if you come back and you've not lost weight, the shape memory alloy around the base will constrict your ability to wear our shoes, beware. We then told her it was a joke, but she was getting rather panicky. Now that £10,000 machine from Cornell leads us to this 3D bioplotter, which allows us to plot into tissue as well as multi-component materials. So the bioplotter is our main device for looking at 3D structuring with up to 5 materials into the same device. And that device then can have electro, photo, and bioactive materials built in the things we try to make. And this is really the beginning of this idea of social manufacturing, democratization of manufacturing and the maker movement, and open source code. Open source code is going to be something that will change an awful lot in relation to the speed at which people update ideas. Is it relevant? Is it not relevant? The answers to that will come out through social networking, and it will come out through the idea of open source. So Cubify, Thingiverse, Arduino, which we use all the time, this idea of shapeways, the MakerBot industry, and Fab at Home, and now 3D Systems, who are nearly gobbling all these little companies up, to give you this idea of social manufacturing, the multiple market of one. Right. Oh yeah, and this is the machine that I let loose the designers on. The little device on the left-hand side there costs the same as a BMW M3, and that's the atomic force microscope, and it's used in a tapping mode by designers in the group. Functional materials that come from those families, to digital fabrication technologies, to integrated devices, to intelligent material systems. And now, here's the matrix of fabrication tools that are now available to us. So we've got these families of materials, and now we have this wide range of possibilities in terms of how do you fabricate those materials into useful products for people. From materiality to the material experience, idea of sustainable platforms, from human biomaterials interfaces to human information materials interfaces, anticipatory medical devices and products inspired by nature on one side, to smarter built environments, and fashion interaction on the other. We'll be faster, I think. A lot faster. Some of the things that we have started to do in the lab works, the postgraduate design STEM interaction studio, putting the human at the centre, new products that resonate with people, going beyond the current state of the art with this kind of equipment and materials, through sustainable lifestyles, preventative and assistive healthcare, independent living through ambient environments, and how we build those, both on the body and around the body. The plus energy home, and fashion concepts made real. The group is set up in like this 200, 250 metres squared of space in Islington, and there's 3 areas really: bio-explore, super sense, and ambient. Design-led and user needs driven, but materials anchored and solutions focused. And just to give you an idea maybe of the skill base, there's the group. So nanoscience, process technology, printed electronics, biomimetic structuring and biomaterials engineering, printed textiles design, fashion interaction, the idea of programmable circuitry and electrical engineering, industrial design, chromogenic materials design, fashion design, and 3D textile design. You need all of these skills to actually get even past the tip of the iceberg in how materials and design interact for a human benefit. You need all of these skills. So, what's actually happening? We're going from smart clothes, which alter their thermal properties, to desktop fabricators, where we are now. The use of biopolymer gels for muscles, tissue, and skin, and then intelligent material environments, and then 2020, atomic customization of materials, ubiquitous use of nanoscience and technology, so the words don't exist anymore, and then smart skin for intelligent clothing and direct human repair. It won't take this time scale. It won't happen by thinking about it over 3 or 4 years. So, this idea I'm trying to get across maybe is design-led, but needs-driven, and materials-anchored approach offers welcome solutions to contemporary issues of consequence for people. design science interactive and non-disciplinary approach is an effective route to elucidating answers. I say non-disciplinary because it's of no consequence then once you get to that kind of 10 sets of skills. It's not about, oh, I can bring this to it, oh, I don't think you need me in this. Every morning in my group, everyone gets together to look at the one problem that wasn't solved the day before for 1 hour, and then goes back to the day job. It is the context of experiencing the aesthetics, functionality and meaning of materials that inspire solutions to lead to implementable products and systems that matter. I should also say that what we do is design as research. It's not design research. I'm not that interested in understanding design better. I'm interested in taking design into solutions for people through materials. Thank you very much.